Hey guys, welcome back to the channel. Today we'll be doing glass refractions in C++ and coding our ray tracer. So the last time we left off, we actually had two metallic materials. So the first one was smooth metallic and then the other was rough metallic, right? So this is what we had from last time, a blue metallic ball, and I don't think it was blue. I think I changed the color recently, and a green smooth metallic. The point is we had a rough metallic and a smooth metallic, right? Today, however, we'll be delving into refraction, so creating a glass material, as I said. And in order to do that, we need to actually follow Snell's law, so laws of refraction and stuff like that. We'll be doing it a little bit differently. So instead of calculating the refracted angle, we'll be actually calculating the refracted ray by splitting it into two components. So we'll have a perpendicular component and a parallel component. These should be parallel to the eta 1, so eta prime, which is the IOR of the glass surface, so to speak, right? Or glass material, so to speak, right? So enough blabbering, let's actually get into coding. Let's open up our ray tracing CPP and let's go to our ray tracer. I think it's already open. Yeah, so it's open. And the first thing we want to do is define our refract function, right? So let's come into our ray utilities.h and then come down to our reflect definitions and then define an f vector refract. It's going to take in the same as the reflect, so we'll take the ray direction, so unit vector, and then a normal, right? So f vector uv and f vector and n. We'll also take in a refraction ratio, so this will be the eta a over eta I, or eta I over eta t, right? So it's pretty much a ratio, so we'll just name it refraction ratio. So let's actually call this, it's going to be a double value, so double refraction ratio, and that's pretty much it. And let's actually define or create a definition in our ray utilities, right? So now let's actually implement the math. If you want to understand the math better, you can obviously Google it or go to Wikipedia, or you could do referencing in Peter Shelley's book, right? So as I mentioned, we won't be actually calculating just the angle, will be refracted angle. We'll be actually calculating the refracted ray in two components. So we have to split that component first, or split the refracted ray into two components and then add it up to join that one vector to get that one vector, right? So yeah, the first thing we want to do is calculate the cosine. So auto cosine, which will be equal to the minimum value of the dot product, so f vector dot product minus uv and we'll take the minimum range in 1, right? So here I'm using f vector dot product. You can actually use uv dot n, so something like this, uv dot, you could also do this, both are acceptable. And next we need to calculate the sine value, but not yet. So the sine value we'll use for total internal refractions or reflections. So we'll actually just do the refraction part right now. So let's actually calculate the perpendicular component. So I'm going to name it perpendicular component of the ray out, or the refracted ray. And the way we do that is actually we need the refraction ratio. So refraction ratio multiplied by uv plus cosine multiplied by n. Okay, so I'm actually going to rename cosine here into a capital. So you might have seen a similar kind of syntax before, and that is we are calculating the point along a line. So we use the start position, the direction plus a increment value. So once that's done, let's actually calculate our f vector, our parallel component, and we will do a minus square root. So minus square root and take the absolute value of 1 minus the squared length of a perpendicular component. Perp component dot square length, and multiply by n. And at last we can just return the value. So let's come back here and just say we add those two components together to get the final refracted ray. Perp component plus our parallel component. So that's it for our refract function. Let's actually go back to our hittable object CPP and give a condition to check if our glass material is active. So let's actually say else if B glass and return normal, right? So we need to actually calculate the refraction ratio first. So remember, we have actually given a parameter for the refraction ratio, and the refraction ratio is actually the ratio between the first material IOR and the second material IOR. So index of refraction. Our first index of refraction is always going to be 1, so the IOR of the atmosphere or air, so to speak. The second IOR is going to be the glass material itself, which we'll declare in our H file, right? So let's go back to our hittable.h and let's declare a IOR value. So you property edit anywhere, bring that down and put an IOR value. I'm actually going to initialize it to 0.2, so we get that nice glass refraction. And let's come back to hittable. And in our B glass, we'll actually define our refraction value. So double refraction ratio. Okay, I think we're naming it over again, but is equal to, okay, so you could actually put IOR here, but we want the refraction ratio to be dynamic, so to speak. So you could actually put 1 by IOR, but that will actually always return the refraction value for the ray outside entering a glass value, right? So imagine this, we are actually calculating instances where we have two instances actually. One is the light ray entering from outside the glass material, so from the air to the glass material, and also when it's leaving the glass material, right? So when it's leaving, we'll actually set that to IOR. So we need to calculate that by understanding or identifying when a point is outside our glass object itself. The way we do that is actually quite complicated, so to speak. So let's actually define front face here. So pull front face, and not here. So let's actually come up to our scatter function and we'll define a give another parameter actually. So bool be front face, and it's going to be an optional parameter, so let's actually give it to true, or rather not, because we're actually calling the scatter call just once, so we don't have to make it optional. And let's come back to a hittable object header file and then declare the same, be front face. All right, so that's it. And now we need to calculate if we are outside or inside an object, right? So there are a couple ways to do this. Obviously in Peter Shirley's book we use mathematical formula to get the inside or outside an object. I think it's pretty much the same thing we'll be doing in today's episode. We'll be using line tracer and doing double checks. The same thing was used in Peter Shirley's book, but instead of doing two line traces or shooting two rays for just one calculation, I think he used a square root formula. Like if there are two roots, that means you're outside a circle or a mesh. If you have just one root, then you're inside an object. So using that, you can actually reverse your normals and then get inside and outside an object. So if you're outside, then B front face will be true, and if you're inside an object which will have just one square root, you'll have B front face is equal to false, right? So let's do that. An equivalent to that is actually, let's come back to our ray trace CPP, come back to our render call, so, or the ray color pretty much, not the render call. So here we need to do one thing, right? So let's actually come up to the top. The first statement we're going to do is we're going to say num hits, right? We're going to say 0. So num hits is pretty much the number of hits, right? And the first number of hit will actually increment in the first hit of our ray. So when we're shooting the rays through the pixel centers, we'll hit an object and that time we'll increment it by 1. So num hits plus plus, right? And the next incrementing will be done with a additional line trace. So we can actually come down here. Let's actually come and say if get world line trace by single channel, and then do the exact same thing but with offsetted positions. Now you might be tempted to go with get world here, but it actually poses a lot of problems, because get world actually hits every object in the world that is obviously having a collision. This is not what we want for a second line trace essentially, right? Because when you think about it, let's say we have two objects here, so touching each other, right? So I'm going to keep it this way, right? So let's say the first line trace actually hits the object, and then we start the line trace at the hit point, and then we shoot it towards the direction. So from this point to this point, right, essentially. So we're shooting it in this direction, right? So let's say there's another object here. What happens is, even if we are inside the object, when it hits out, we'll actually calculate this object as well. So now instead of having just one hit, we'll have two hits, right? So it's an even number of hits, which will return the front face being true, which is not what we want. We only want to calculate our line traces for the specific actor, which is the actor that the first line trace hit, right? So we can actually do that pretty simply by saying hit result dot get actor, and then we can draw a line trace to that actor, right? So only to that actor do we draw line traces. So line trace again. So let's do that again and let's say line trace. So actor line trace single, this only does the hit check only to our actor, right? So let's do that, and we can actually give our parameters now. Let's create a different hit object. So let's say f hit result, and I'm actually going to type in a actor hit result. So actor hit result, and then we can give that as parameter actor hit result. We're actually going to calculate a couple of different positions, so let's actually calculate them as well. So start actor or actor start makes sense, is actually going to be the impact point. So hit location plus an offset. So we need a little bit of offset, otherwise, let's say if the line trace hits a surface and then we start from that surface, the line trace again going to hit that surface and return the exact point again. So we don't want to do that. We want to increment it just a little bit inside the sphere or the object. So we'll actually add a small increment. So let's say ray direction multiplied by a very small amount, so the same as before, and then we can say the actor end result, which is actually going to be the same thing, actor start plus the ray direction multiplied by in 32 max, right? So in 32, and we'll give a max value. So that is one way to do it. Let's come back and give our necessary parameters. So actor start and actor end. We can also give in the ECC visibility and our same collision parameters. We don't have to change it. So once that is done, we can just increment our number of hits, so plus plus. Right, so that pretty much should be it. And let's come back to our hittable object, or a ray tracer actually, and in a scatter call, so we're giving the hit actor dot scatter call. We're not giving the front face boolean, so we'll calculate the front face actually. Let's actually come down before the attenuation, and let's say let's actually give a boolean here, right? So boolean is front face, so just so we have the differentiation, and I'm actually gonna give it to true, because obviously when we start we are outside a sphere, right? Or I keep saying sphere, but it's actually mesh or an object, so keep that in mind. If I said sphere, it's an object, right? Sphere is equal to object. So the way we're going to do this is by checking if num hits modulo 2 is equal to 1, then odd number of hits. So then we are actually saying front face is equal to false. Right, so that's pretty much it, and we can just give the front face here is front face, should be fine. And let's come back to hittable, front face, scatter, ray direction, IOR. So let's come back to our else if statement where we ask if our object is glass, and let's define our refraction ratio. So we'll use a ternary operator. We'll say the bool, so b front face. If it is front face, then 1.0 divided by IOR. If not, then IOR, right? Okay, I think that should pretty much be it. So let's actually call the ray utils function again and call the refract function. Let's give in the UV or the ray direction, the normal, and the refraction ratio. Refraction ratio. Okay, so now let's build this and check if we have any errors. So it's built. Let's come back to Unreal Engine, and then let's get rid of that. Let's try a ball first. So let's actually in a hittable object, let's convert the type to hittable glass, and then set an IOR to 1.2. So that's the default value. Let's try this. So yeah, we have a glass-like material, but obviously we have some kind of bug going on. We have double reflections here, this point. I think that has to do with, if I come down to my sphere mesh and double click on my static mesh, I think the problem here is if the ray is actually starting to go inside the sphere, right? So the ray, let's see if we are looking at the point of view of the light ray. So we start here and then we hit this point, right? Now we are actually incrementing the point by very small amounts. So we hit this point and then we go inside a little bit, right? And now we are shooting the ray in the same direction inside the sphere. So we are going in this direction. Now there is no guarantee that the ray will hit this object because the collision is actually outside, right? It's just bound to the outside of the sphere. There's no collision inside the sphere. In order to get the collision inside the sphere, we actually have to come down to our collision settings and activate double-sided geometry. So click that on. So now whenever the ray goes inside the sphere, there is that collision mesh or the collision to reflect the ray trace or the line trace. One more thing I want to point out is that if you're trying to do this in Unity or any other game engine, make sure that the normal is being positive all the time. So the normal should always point against the direction of the line trace or the ray. So if the ray is coming in this direction, the normal should be always pointing outside the ray direction, not inside. If that happens, you might have to inverse the normal, so negative that. And if you do that, it should work pretty much the same as this, right? So let's save that and let's come back to our object and let's see if you have any difference. Yeah, so now we have that glass ball look, right? So this is what we want. If I come down low a little bit, you can actually see the horizon being warped around, which is what we need, right? So yeah, we have that horizon or the flow being inverted. So the flow is actually up and the sky is actually down. So this is how glass works in real life as well. And one more thing you have to notice is that glass actually barely puts some shadows. So that's actually fine. We'll also do another instance. So let's come back to our ray tracing CPP and actually introduce a total internal reflection or reflection, sorry, total internal reflection. So not all times does a glass material refract, okay? There are some instances where the glass material actually decides to reflect the ray. So that's what we'll be doing. In order to do that, we'll actually come back to our refract method and then define a sine value. Auto sine is equal to the square root of 1 minus cosine into cosine multiplied by cosine, right? And once we have that, we can actually say another bool value and we can say cannot be refract, right? And we can actually calculate it by saying the refraction ratio multiplied by our sine value. If it is greater than 1, then we cannot refract. So if B cannot refract, then return a reflect value. So return reflect. And we'll actually give in the same thing. So UV and N. So let's build this. So we have a successful build. Yeah, so we barely notice any differences and that's fine. Let's actually position the monkey right behind a glass sphere to see if you have any transparency going on, right? So let's actually give this color a green, that's fine. And let's try looking through the glass material. So yeah, it works. We can see our glass monkey or our metal monkey being distorted heavily by our higher index of refraction. So if you actually reduce the index of refraction, we can actually see the monkey a lot clearer, a lot clearer. So let me actually put 1.04 and also reduce the amount of samples I'm doing here. So it's actually at 20, let's actually put it at 20, it's at 30. So now the render should be a little bit quicker and hopefully we can see the monkey a lot clearer as well. Yeah, so it works, right? The monkey is being distorted, not heavily, but we can see the glass effect taking shape. The last thing we could do is actually introduce variable reflections. So when we look at a window at a steep angle, so if I'm looking the window straight ahead, I could actually see through the window. But if I see at a steep angle, it'll turn into a reflection kind of material, right? So we can actually do that with a simple polynomial equation called, I forgot his name, I think Schlick, right? So it's called Schlick's approximation. We can actually do that. Let me quickly copy that because I'm not going to do it by code or by hand. So let's come back to our ray utility CPP and then come down and declare a function or define a function. So this is what we are dealing with, right? So this whole equation is called Schlick's approximation for reflectance, right? So we'll actually define this inside our H file. F vector, and that should be it. Or rather, no, I think it's a Boolean value, right? Yeah, double value. So double reflectance and cosine, that's fine. Now, in order to check, we actually need a random value between 0 and 1, which we can actually do pretty simply by saying double random, and then we can call our random number generator random double generator in range, and we can put 0 and 1 pretty much. So we can come and check, or reflectance, and the input is actually going to be the cosine value we just calculated, and the ref IDX is actually pretty much the refraction ratio, right? Is greater than random number, is greater than the random number, then we reflect. So let's build this. Again, if you guys want to understand more about Schlick's approximation or the refract function in general, you can actually go to the description. I'll leave some resources down there for you guys to follow along. So once the build is complete, let's come back to our Unreal Engine and try rendering this out. Yeah, so it works, right? The variable angle reflection I'm talking about is when you look at the edges of the sphere right now, so you can follow along with the edge, and we can see more reflections on the edge compared to the center, right? The center is more of refractions, but the edges are more like refractions or reflections, right? So yeah, it works. It looks like a glass ball to me, so I think let's leave it at that. And yeah, we can actually change the monkey to be a glass as well. Let's check the monkey to be glass, and then let's render him out. And one thing you might have to keep in mind is when you have high color values, you might not actually see that refraction going on because the color of the monkey or the object will absorb or add to the color of the previous refraction. So you'll have much more of a black color. So for example, if I crank this up all the way to red, right, or pink, and I bring this monkey back here, so maybe down there, and turn him up a little bit, you might actually see him become more darker. So let's give that a go. And yeah, so this is what I'm talking about. You might be freaking out. Okay, we have two problems actually. The first problem is obviously the it's pretty much a side effect. I won't say it's a bug. It's like we're absorbing the color from the previous, so it's red, and then we add green and red to it, right, on top of it, and we're only sampling in 0.5 increments, so it becomes blacker. I don't think we're doing 0.5 anymore, but since we're adding, it becomes blacker, right? So keep that in mind. The other problem is the monkey looks hollow at the moment, and that's because we haven't turned on our double-sided geometry in Suzanne Monkey. So let's open the static mesh component and come all the way down to collision, and turn on our double-sided geometry. And let's save that, and let's try rendering this again. Yeah, so the monkey now is reflecting properly or refracting properly, but we still have that black color absorption thingy going on, right? and it's fine. I don't mind it at all. Let's actually reduce the IOR and see it much more profound in action. If I actually crank down the saturation value, you might actually be able to see the original color of the reflected or the refracted object intact, right? So let's run that. Yeah, right. So if you like reduce your saturation value, you might have more of that uh, original color retained. So if you want to see that full color range being reflected in your glass or refracted in your glass, a simple solution is simply to come to a material color and then put it to white, right? Yeah, so now we can see the green monkey more visible in the glass monkey. Another cool thing you can do with glass materials is you can have polished diffuse materials. So let's actually duplicate our glass monkey and then resize them just a little bit. So maybe like that. And the inside object is actually going to become a diffuse material, and then the material color is going to be some yellowish color, right? So now what will happen is we'll have a polished coat on top of our diffuse material, right? So yeah, that's not what I'm talking about. Let's actually increase the size a lot, just a little offset. So yeah, maybe that will do. Yeah, so that's what I'm talking about. We have that smooth polished look on top of our diffuse material, and it looks like somewhat of a smooth plastic, if that's what you want to call it, like a really smooth plastic cover or something, right? Yeah, it looks pretty good for now. And when we add lights, it'll actually look more pronounced and more polished. So that's pretty much it for today's video. If you guys found it informative, entertaining, or educative, make sure to leave a like and consider subscribing. It really helps me a lot to stay motivated to create more videos on the same series. With that said, I'll see you guys in the next episode.